Okay, here we go.
We're starting from the beginning.
We're going to start at the very beginning. I'm going to answer any questions that you have. Hopefully you've gone through the other videos and have found out what you need to, but I've taken pictures of your study guide. We're going to go step by step through it. Excuse me. If there's any questions, I will stop. I will go over it. Okay? So I want to make sure that we get through the whole study guide, that you're able to understand. We might not get through the whole one today. We'll finish it up next time. But I want to make sure we get through the whole study guide before you have the test, okay, which is a week from today. So I'm going to flip this to the side. All right. So the first thing that we talked about in this unit was physical states of solution, a solute, a solvent, solution. Did we have any problems with section 1? Anything you want to go over? Are you able to classify things as solutions or non-solutions? Okay, so a solution is something that mixes very well. And a solution is considered very small particles. Okay, we're going to get to later on when we talk about a colloid. A colloid has bigger parts or particles in a what we would call a mixture. But when you shine a light through a colloid, it will scatter, sort of like if you shine headlights through fog, it will scatter. So it's not a true solution. It's what we call a colloid. If the particles get bigger, we get what's called a suspension. You remember when you had amoxicillin as a kid and your mom had to shake it up? It was a pink medicine because it all settled at the bottom before she gave it to you. That's a suspension because after time it falls out. So thinking of the Tyndall effect, and the Tyndall effect is when I shine lights into fog and it scatters. Foggy air, there would then be a solution or a non-solution? Non-solution. What about tears? Solution. So I'm just going to go NSS. What about maple syrup?
Oh.
You can see through it. What do you think is going to happen when we shine light through it, though? Okay. Well, we're going to do a lab, so I'm going to just put this right now because we don't know. Okay, depending on the particle size, that's a big thing, depending on the particle size. So depending on what maple tree you got it out on, how many particles are in it, if you did real maple or if it's just maple flavoring, there's a big difference. Okay, so what about milk? Why would you say solution and why would you say non-solution? Okay, so it's going to scatter light. When I try and put a flashlight up to milk, it's going to scatter the light and the whole jug's going to actually light up. So it's going to be a colloid. So we're going to do a non-solution there. What about creamy hand lotion? Non-solution, because it's probably going to be a colloid or a suspension, right? Okay, and of course we would make a key. This is solution, this is non-solution, so we knew what we were doing. Okay, going on. Solubility. All about demonstrating how, there's a lot of words with this. So soluble, insoluble. Immiscible, miscible. Solubility, saturated, unsaturated, supersaturated. Do we have any problems with that? Okay, easiest way for me to remember miscible is it mixable or is it not mixable? Immiscible means not mixable. Okay, so miscible means it'll mix, immiscible means it won't. Okay. Saturated, I've put in as much at that temperature as I can put in. Okay, temperature is the key thing here. Unsaturated, I haven't put as much as I could at that temperature. And supersaturated, I have actually heated the solution up, put in as much as I could at a higher temperature, and then cool the solution down. Really fun thing to do with this is to get about 1 liter of vinegar, put in about a teaspoon of baking soda, and then let it heat up for a long time until you get like it looks like a skin on the top. Quickly pour it into a clean container and let it cool. And then you can take and just put a crystal of baking soda on a plate and pour it onto it, and it'll make a stalagmite. Actually, what we call hot ice. It takes a long time to boil it down, and it stinks pretty good. So from your book, you should have been able to get this table, which is basically tells me what is soluble, what is considered soluble and unsoluble. Okay, so hopefully if you haven't, you can go look in your book for this. Okay, you should be able to, being given something like this, tell me if it's soluble or insoluble. So you should have this in your brain. Okay?
From number 2, how would we cure?
Okay, so we would say 1 milliliter to 25 milliliters is 0. What? 0.04. Okay, and so that would fit into the less than 0.1 per 100 milliliters, which would be not soluble, right, or insoluble.
Wait,
So,
isn't it? Oh, wait.
okay. So all you have to do is just take the grams and divide it by the grams of water. Or if it's milliliters, milliliters by milliliters, and see how much you've got in there. What percentage? Huh? It just is at that temperature. If it changed from that temperature, it's going to change how much I can dissolve.
How would you label that?
There's no label. They drop.
So for like number 2, we just get the 9 divided by 100 grams,
Mm-hmm.
and then the temperature doesn't.
It just means at that temperature, that's how much I can dissolve. If I change temperatures, that changes. Okay? So then I find this and I find out where it fits here. Is it considered soluble? Is it considered insoluble? Okay, that's not very many grams. That's 0.80 and then a 9. So that's not very many in 100, so it's probably going to be less, which is insoluble. Now, stating it's insoluble doesn't mean that nothing's dissolved. That's important to know. Stating it's insoluble does not mean nothing's dissolved. It means not very much is dissolved. Okay? Okay, a solution when a small piece of solid is added causes more solid to come out of solution. What are we probably then? We probably got a supersaturated solution. So that's a solubility term we'd use there, would be a supersaturated solution. Okay, this would be unsaturated. This would be very unsaturated. Okay, so I was looking at this graph here. You need to be able to read graphs. And this is all about reading graphs. So I'm going to use green here, or maybe red, easier. Okay, so if I start at 55 and go across at 55, whoops, I went up a little bit. Okay, and if I could start at 35 and go up, where these two cross is above the line for KNO3, which is right there, right? So in order for this solution to exist, it's got to be a supersaturated solution. Okay, so I've got to heat it up to a higher temperature and then cool it down. Otherwise, it's beyond saturated. I've got solid left in the bottom. So you need to be able to tell me, looking at a graph, what's happening. Have I got a saturated, unsaturated, or a supersaturated solution? Okay.
So if it's below the line, so
Okay.
how they can't.
If I had come like the KCl here and I come across at 25 and down, this right here would be an unsaturated for KCl, which is right here. If I had something that actually hit on that line, that's saturated. Above that line would have to be a supersaturated solution. So for KNO3, anything this side of the line right here, that would be supersaturated in order for it to be that way. Otherwise, it would, on the line would be saturated, below the line would be unsaturated. Yes? Okay, so, and they might just say, okay, I have this many grams, and this is how much I can dissolve. Is it saturated, supersaturated? They might just give it to you in words rather than give you a graph.
Can you do one more about
Yeah, you bet. So let's look at NaNO3. That's that very top one. I'm going to use the blue. So I've used every other color there, basic one. So we're looking at this line right here. So it asked me at NaNO3, 82 grams. So I'm going across right here about, okay, and what was my temperature? 10 degrees. Coming up at 10 degrees right here. I'm going to be up above the line, so I am supersaturated, okay? Now, if they ask me, could I dissolve that much at that temperature, what would the answer be? No, I can't, because I have too much In order to get it dissolved, I'd have to get it at a higher temperature and then cool it back down. So if they ask me, could I dissolve that much at that temperature? No. I can dissolve some at that temperature, yeah, but could I dissolve the whole 82 grams at this temperature? No. Okay? All right, going forward. Determine the following is miscible or immiscible. Remember, miscible means mixable, and immiscible means not mixable. So 25 milliliters of cooking oil and 25 milliliters of vinegar. The resulting mixture is cloudy and slowly separates. What term do I use? Immiscible. Good. So that's the IM. Okay, that's the last time I'm going to dry that. Okay, next one. 25 milliliters of rubbing alcohol, 25 milliliters of water. The resulting mixture is clear and colorless. Miscible.
How would you know that they're both clear? So how would you know if they're separated?
You actually, when you have two clear substances, if they don't mix, they'll actually make a line, and you'll be able to see that. Okay. 25 milliliters of chloroform and 1 gram of roofing tar. The resolving mixture is clear but dark brown in color. Miscible, they mixed. Okay, so here we have a solution problem. We're now to 7.3. Predict the general way the solubility of solids in solvents on a basis of molecular polarity. So hydrated ion just means that water is attached. What does that mean? That means like what we did on our last lab where we had .7H2O. That's known as a hydrate. Okay, but it means waters are attached. When I have a salt that dissolves, we actually get a hydrated ion, either a cation. Actually, we get cations and anions that are hydrated. So what happens is a cation is what? Positive or negative? Positive. So what we have is we have water coming along, and water has an oxygen, and it has 2 hydrogens attached, right? Oxygen actually has a little bit of a negative, and the hydrogens have a little bit of a positive charge. So the water orients itself so that the negative oxygen is closer to the positive cation. So we end up getting this kind of thing going on here. Whoops, I missed attaching. Make that oxygen a little bigger. All right, so over here, an anion is what? Positive or negative? Negative. So as the waters go to attach to the anion, the little hydrogens are more attracted than the big oxygen. So here's my big oxygen, and I would put my little hydrogens attached. Remember that my oxygen actually has a slight negative charge that we use a small delta, and my hydrogens have a slight positive charge. So if I do some more here, I'm actually going to use a bigger, be easier to do for the, whoops, I got that one backwards. Tried to use a big one and did it backwards. Actually bring my waters in, or hydrogens in as. Okay, so it actually would orient that way. All right, moving on. So good rule of thumb is for a solvent, what blank dissolves blank? Sort of. Like dissolves like. Good. Okay, be careful not to confuse blank, solute blank with blank, at which a solute dissolves. Good. Solubility with rate. Okay. What can you use to help rate increase? Heat. Making more surface area. Movement, like as in stirring or agitation. Okay, and those are our 3. And down the bottom we have exo and endothermic. That's way from the very beginning. Exo is give off heat, endo is taking in heat. Okay. All right, here we have some molecules. We need to be able to look at a molecule and be able to see if it's polar or nonpolar, because like dissolves like, and if we don't know if they're like, how do we know if they're going to dissolve if we don't just do it in lab? So remember that water had a slight positive on this side and a slight negative up top. I should put that positive going across a little better. There we go. So if I look at this first one, nitrogen is actually pulled out because of this unshared pair of electrons, pulled out of the plane, and nitrogen has a slight negative on it, and hydrogens have slight positives. So because of this, I can actually take and cut this molecule, and I have a positive and a negative side. Because I can do that, that's a polar molecule. Well, water's polar, this is polar, so they will dissolve in each other. What about the next one? Nonpolar, why do you say that? There's no unshared pair of electrons to pull boron out of the plane, so they're all in a plane and I can't get boron out. What about carbon tetrachloride? Polar, nonpolar? Nonpolar. I can't get the carbon away with it from the chlorines with one cut. I have to do a circle, and that doesn't count. Okay, what about sulfur dioxide? Polar, because I can do that slice there, and I've got a positive and negative side, you bet. What about H2S, which is rotten egg gas? It'll also be polar because we've got the hydrogens plus, and the sulfur will be a slight negative, so that is also polar. Okay, so then we get down to solution concentrations. Molarity is what we did today with the Kool-Aid lab. Molarity is moles. Let me change colors. Moles of solute divided by liters of solution. Now this is different than what we did in the freezing point lab, because the bottom for the freezing point lab, we were working with molality. Molality was moles of solute divided by kilograms of solvent. Okay, so the way I remember it is I just remember a little ditty. You can remember however you want, but molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Molality is fat. That's just how I remember it, however you want to remember it. I just remember molarity sort of sounds like molitery. Molarity, molitery, that's how I get it in my head. It's moles per liter. Molality makes my mouth go fat, so I just remember it's kilograms of solvent. Okay. All right, so you need to be able to calculate molarity, and basically that's just taking moles, dividing it by liters, and you got your answer. Now, if you don't have moles, you got to find moles first. Okay. So finding moles first, you're going to have to take the 11.9 grams of KBr, add up KBr. Potassium is about 39, bromine is 79, so 40 and 80, 120, take away 1, about 119 grams KBr. Okay. 111.9 divided by 119 is 0.1. Is that right? Somebody help me? I'm trying to do this in my head and it's not working. I believe that's 0.1. Yeah? Okay, that's moles. Then I have to take and divide the milliliters by 1,000 to get to liters, so that's 0.2 liters. That leaves me with 0.5 molar KBr. Okay, everybody having okay with that? Okay, moving on. You got some more samples here. I'm going to let you do a couple by yourself. If you have problems, let me know. When we get to number 2 here, we're using the same equation, just rearranging it. Now we're looking for moles of the solute. So remember, we have molarity is equal to moles divided by liters. If we're looking for moles, then we're rearranging it so molarity times is liters. Okay? This is going to be important because if we need to make up a solution, we need to find out how many moles and then change the moles to grams, because we can't weigh moles, but we can weigh grams out. So on this one, all you're going to have to do is just go moles are equal to 1.75 liters times by 0.215 molar, and I've got my answer done. Okay? Now, the next section down here, number 3, they ask us now about liters. So you're going to rearrange this equation a whole bunch of times. So molarity, remember, moles divided by liters. So if I want liters, which is on the bottom, I'm going to times through by liters and divide through by molarity, and I get this. So it's just rearranging the equation. Okay, again, you got to get into moles first. So now these, you got to change from grams to moles, and you're going to get your answer. Okay, we'll start here next time. Please try and get as much done as you can on your own. I'm not necessarily going to do all of them each time, okay? We will have a small quiz next time.